Okay, hey everybody. So today we're going to be talking about the central limit theorem and confidence intervals, more specifically other stuff, but we'll get into that. But first I wanted to talk about where you can find your project feedback. So how the project feedback will work is because y'all worked in groups of 2 or 3, only after the last person has finished their review, you'll see the project feedback by the end of day of whenever that last person's review was. So if you have 2 people working and one person had their review yesterday, one person has a review next week, you'll get your results back or your feedback back that day next week. So where do you find that? Let me actually do a quick example. In this phase 1 project here, let me just do a random assignment real quick. Oops, what's all this random stuff? Yeah. Okay, hold on. I have to put in a sample assignment in order to see it. What random PDFs do I have? Okay, let's do this then. Okay, so you've submitted your project. When, oh, cool, I didn't know they did that. When it's submitted, you click onto submission details and then just click on show rubric. And show rubric, if this was one of your projects, you'll see a bunch of my comments under the rubric here. I'll tell you now, I am known to be a pretty easy grader, but usually, if you take a look at these rubric points, you don't really have to do too much to get the exemplary stage. So even though you'll see a bunch of 3 points, I think most people will get everything 3s. I do write my feedback and comments in bullet point form of what I do think you can still work on. So do take note of that. Don't see a 30 out of 30 and feel like you did a perfect project. I mean, all your projects are great, but there is always room for improvement no matter what. So look out for that. Any questions about where you see your project feedback? Also, you'll get the same feedback for every person in the same group. And if there's anything that I am, if there's a comment directed to a specific person in the group, I will make that note as well. So you will see that there. So questions about seeing your project feedback? All right. Okay, so that's the only thing I wanted to talk about before we get into our topic for today. So today we're going to be talking about central limit theorem and confidence intervals. I have restructured it a little bit in a way that I think will be easier to get through. So we'll be talking about slightly different things. First, we're going to actually talk about our first statistical test, because I think this connects really nicely to what we talked about at the end of yesterday. We'll be talking about the one sample z-test. And then we'll talk about the central limit theorem, talk about sampling and what that's all about, confidence intervals, and the t-distribution. So these will be the things that we'll hit today. Some things, especially towards the end of today's presentation, will be left a little bit open-ended to be continued next Tuesday. So just in case, I'll also mention like what these loose ends are, just so you all know. Actually, before I get into this even more, I wanted to point you all to a really, really great resource. I put this down here under phase 2. There's a brilliant YouTube channel called StatQuest. I don't know if anyone's heard of it, but StatQuest is an incredible YouTube channel. It's this guy who I think he used to be a professor in North Carolina somewhere. And he explains a lot of these statistics fundamentals with the context of data science in mind. So they're each like, there's a range, I think they range from like 5 to 20-minute videos. And they're on very, very specific things. So if you wanted like a deep dive, and I think he explains it very clearly with all of these like cute little Microsoft Paint-esque animations, I highly, highly recommend. Like I studied stats in college for years, but it was through watching his videos over and over again that like it helped me understand in the context of data science why these are important. So I really do recommend this playlist if you just want like another video resource. Okay, so back to these slides. All right, let's start with statistical tests. So each of these statistical tests that we're going to be doing, today's session, we're going to be talking about tests Tuesday and Wednesday next week, we'll be talking about more tests. For all of these statistical tests, there's a lot of facts to remember about each of them. So therefore, in our resources Google Drive, if you ever wanted like a one-stop shop for all of the stat stuff, so from yesterday, I went in and I added like the expected value and variance formulas, and I like circled the more important ones. But there's also this one that I created, this PDF here, that talks about all of the tests that we are going to talk about, what they're used for, what the conditions are, and all of these things that we will talk about later. More importantly, I give you the one-line Python code to run this test. So if you ever wanted to look for how to do these tests in Python and when to use what test, feel free to consult this. And it is in our resources Google Drive in phase 2. Okay, so let's set this first test up with a scenario. So a data scientist wants to examine if there's an effect on IQ scores when using tutors. To analyze this, she conducts IQ tests on a sample of 40 students and wants to compare her students' IQ to the general population IQ. So these 40 students are tutored, and the general population, you can assume, mostly isn't. So the way an IQ score is structured, we know that a standardized IQ test has a mean of 100 and a standard deviation of 16. When she tests her group of students, however, she gets an average IQ of 103. So based on this finding, does tutoring have an effect? So several things going on here. The worldwide, I guess, average known IQ, it has a mean of 100 and a standard deviation of 16. If this person is testing this group of 40 students and taking their average IQ and finds that their average IQ is 103 versus 100, a non-stats person would be like, cool, 103 greater than 100, yes, tutoring does have an effect. There is a chance also, though, that these 40 students that you're taking can just so happen to have higher IQs on average. So we're doing the statistical test to see how likely is it that, you know, one, this 103 isn't by random chance. Remember, we talked about, did we talk about p-values yet? Yeah, we roughly talked about p-values a little bit yesterday, but we'll get back to this in a little bit. But this increase in IQ of 3 points from 100 to 103, is that statistically significant enough to say that tutoring does have an effect? So to solve this problem, we're going to use the statistical testing process. Now, this process is a process that we're going to use for every single one of our statistical tests that we're going to talk about. So if you actually take a look at the statistical test PDF that I put here, the steps are exactly the same. And all of these tests that we're going to talk about over the next few study groups, they're all going to follow this process. So this process, I would say there are 6 steps, but I would say there's like 3 main portions. So let's talk through these steps together. So steps 1, 2, 3 are in the setup of the experiment. So we're going to set up our hypotheses, pick the statistical test based on your experiment, and also pick your alpha. I'm going to go through these with our example in a little bit. Next, you have your calculation step, which is really just these 2 over here, your calculation steps, and then interpret. So there's a good bit of setting up to do for each statistical test. We're going to calculate some stuff, and then we're going to interpret. All right, so let's get into it with our actual problem. Oh, I guess we'll start with setting up hypotheses. Okay, so every experiment does start with a null and an alternative hypothesis. So our null and alternate hypotheses for this problem here, and let me just draw this out. These are down here. So typically, the null hypothesis represents no effect. And so you can see here, there's 2 equations down here. This represents our null hypothesis, H with a little 0 at the bottom. In math, we call it H sub 0. And then for our alternate hypothesis, we have H sub A. You might see it as H sub 1. So instead of an A, you might see like a little number 1. Same thing, interchangeable. So just in case you see a couple different versions. This is our alternate hypothesis. So typically the null hypothesis represents that there is no effect. And you can see here in our hypotheses, we're comparing 2 letters, but X bar and mu. Mu is our overall population, and X bar is the mean of our sample. So the null hypothesis is saying that the mean of our sample is statistically the same as the mean of our population, that this 103, yes, it's 103, but statistically, no different from 100. This alternate hypothesis says that there is an effect. And I actually need to make a correction here real quick. Let's see. I want to make a correction that this should be strictly greater than. Oops. Let me see if I can make this a little bit clearer. Okay, so this is strictly greater than, not greater than or equal to. So the alternate hypothesis here is that the 103 that we calculated of our sample is statistically greater than the 100 of our mean. So these are our two hypotheses. And usually, no matter what it is, if you're testing for an effect or if you're testing to see something is different, that would be the result of the alternate hypothesis. In thinking of this as well, and thinking of hypotheses, we have to talk about whether things are one-tailed or two-tailed. Now, whether something is one-tailed or two-tailed does depend on the way that the experiment is set up and also what you're testing for. In this case, we're doing a one-tailed test. One-tailed meaning that we care about whether the IQ increases. If it were two-tailed, they would have phrased it something slightly different. They would have maybe phrased it as IQ is different. So for example, we'll have a couple of examples in our next study group where you're testing the effectiveness of a drug on, I don't know, blood pressure, for example. You're testing the effectiveness of a drug on blood pressure. Yes, you usually want this drug to make your blood pressure go down, but just in case you want to account for maybe this medication might not work as it should and the blood pressure might go up. In a scenario like that, you're doing a two-tailed test because you're just testing for whether people who are taking this medication have a different blood pressure versus strictly greater than or less than. And in this case, we're just looking to see if your IQ increases as a result of tutoring, whereas in other situations, you might just be testing for a difference. So that's the difference between a one-tailed and a two-tailed test. Today, we're just going to talk about the one-tailed test, but the next study group, or I forget, two after this one, we'll have an example of a two-tailed test. So just for terminology's sake, for tutoring to have an effect, we want to reject the null hypothesis. So we want to reject this hypothesis that the X bar of 103 is equal to the population mean of 100. So if we are able to reject that they are the same, that means that they are different. Just in terms of stats terminology, you reject the null hypothesis. You never really accept any hypothesis. That's just how stats is. You never accept the hypothesis. So if you're ever explaining anything in stats, you always say reject or fail to reject. That's the terminology. And just to refresh our data, refresh the numbers on the data that we have. This is our population numbers, a mean of 100, standard deviation of 16. And in our sample, we have a sample mean of X bar, usually X with like a bar on top, of 103 and N being equal to 40 because we tested on 40 students. So this is our hypothesis setup. And remember that these are the numbers that we have. Questions about this setup here? Okay. So we're going to talk about picking the test and also our alpha. So the test that we're doing today, because it's the first test that we have, is a one sample Z test. We're going to come across other tests in the next coming study groups, but for now, conditions that you need to know to do a one sample Z test, you need to know your population mean and your population standard deviation. Just to contrast, a couple, or actually the other statistical tests that we're going to talk about later, you actually don't know your population standard deviation. So the condition for doing a one sample Z test is that you do know your population's standard deviation. Okay, so alpha is also something that you define before making any calculations. Alpha is your cutoff value, and it's your threshold for rejecting your null hypothesis, typically set at 0.05. So your alpha set at 0.05 is, you can sort of think of it as you're looking for p-values lower than 0.05. I'll get to p-values in a little bit. I shouldn't have said that yet. But anyways, usually your alpha is set at 0.05. Another way at looking at alpha is looking at confidence level, which is just 1 minus alpha. And the way that you say and interpret your results with respect to alpha is you can say, with a confidence level of 95%, we can reject or fail to reject the null hypothesis that blah, blah, blah. So here we set up that we're doing a one sample z-test, and then the alpha also determines our confidence level. So if you do have a lower alpha, you actually have a stronger confidence. Later, I'm going to set up some diagrams and we'll see why that is in relation to the p-values that we were talking about yesterday. The standard normal PDF is what we're going to be looking at, and z-scores as well. All right, questions at this stage? All right. So our calculation stage, there's a lot going on here, but let's break this down. So for any statistical test, there is a statistic that you usually have to calculate. If we look back at that doc again, and I'm really only going to talk about this like very generally, every test has a test statistic. So for every test, we have this test statistic, and it just so happens that for a z-test, the z-score is our test statistic, which is great because we talked about z-scores yesterday. So based on the data that we have, again, 116 for our population, x bar 103, n equals 40, we can use our z-score formula to calculate our z-statistic, our z-score, sorry, which is the test statistic. As I briefly mentioned this yesterday, but remember how z-score is x bar minus mu divided by standard deviation? When you are calculating the z-score for a group of observations, you just have to divide the denominator by the square root of the number of things you have, the number of observations. So therefore, we plug in all of these numbers. We have 103 minus 100 divided by 16 divided by the square root of 40 gives us 1.19. So this group of 40 students has a z-score of 1.19. If you remember from yesterday, the way that we interpret this 1.19 is that this group of students lies 1.19 standard deviations away from the mean of 100, and standard deviation being 16. Okay, so with 1.19, I also talked about looking at the associated probability from the z-table. So if we pull up the z-table real quick and we look up 1.19, z-scores can also be negative, by the way. But if we look at 1.19, we have 1.1 over here, and 9 is the last value over here. It's pretty small on your screens probably, but this says 0.883. So the associated probability here is 0.883. So therefore, with a z-score of 1.19, this shaded area to the left is 0.883. Right. So that's just saying that the average IQ of the tutored students is greater than 88% of the population. For p-values, for a right-tailed test, you actually have to take 1 minus this probability, which is 0.12, which is greater than our alpha of 0.05. I'm going to use a diagram to explain this in just a little bit. But any questions about calculating this z-statistic, z-score statistic, and also getting this probability? All right. So now that we have like our z-score and we also have the associated probability, the work that we have to do now is we have to interpret whether this difference, given our confidence level and given our alpha, is this statistically significant? Is this difference, is this z-score of 1.19 statistically significantly does this z-score make our sample statistically significantly different from our population? So I'm going to use this to explain. So over here, we have our standard normal curve. So this is the curve where we're centered at 0 and the standard deviation is 1. This is actually for a z-statistic of 1.19. So basically, this division between the red and the blue is this line there that represents where our sample lies. And we just want to figure out is where this sample lies, is that statistically significant or not? Our alpha is some sort of threshold. When we set an alpha of 0.05, this is kind of what we mean. So here, I mean, you can see that this alpha is here, but a way that you can also interpret alpha, and let me just grab a nice color to do this. Here, the way that we interpret this alpha of 0.05 is that this area out here is 0.05. So if you remember, this one's 0.05. I'm gonna make this not so thick. All right, this is 0.05. If you remember the associated probability with a z statistic of 1.19, this is 0.88. Therefore, this blue area here, which is actually our p-value, is 0.12. So how do we interpret all of these numbers together to make our conclusion? This alpha is basically our threshold for something to be significantly different or not. So if you think about it in terms of number of standard deviations away from the mean, if something is more standard deviations away from the mean, it is significantly more different. So just by thinking about it that way, if a sample happened to be all the way out here, then yes, it's very, very different from the mean. Tutoring does have a pretty strong effect. The fact that that sample ended up here, closer to the center in relation to our alpha value, that is actually saying that tutoring did not have a statistically significant impact on the student's IQ. There's a lot of things going on here, but does that make sense? And does anyone have any clarifying questions here? Okay, so in interpreting your statistical results, there's two ways to do it. The first way is to compare your z statistic. Z stat is what I'm going to say. All right. So here we calculated that we have 1.19 as our sample z. You can actually also find out what this z statistic is. You kind of have to reverse this and figure out where does alpha need to be, or where does the z-score need to be such that this is 0.05. So I'm just going to quickly show you how you do that, if you just excuse all of this writing first. But if you take a look at the table and try and isolate and find where 0.95 lies, because if this is 0.95, this will be 0.05. If you look for 0.95 here, you'll basically see that it will roughly be 1.64 or 1.65. So the associated z-score with a 0.05 alpha is 1.64. So going back to here, you have 1.19 and you want to compare that to, let me just draw this, compare that to 1.64, and you can compare these. That's one way to do it. The other way you can do it is using p-value. So p-value, or your probability. We start with our alpha of 0.05, and then we ended up looking up our associated p-value. So this p-value that we had to start was 0.05. We want to compare that with our area here of 0.12. So there's two different ways that you can compare. These are all equivalent, like this 1.64 is associated with 0.05. This 1.19 is associated with 0.12. That's super confusing, but you know what I mean. So there's two ways that you can do this. You can either look at the z statistic or look at the p-value. Both will give you the exact same conclusion that tutoring does not have a strong enough effect. Typically through Python, we look at the p-values because when you have a p-value, it automatically does, the fact that we started with 0.88 and then we had to split that around. Python automatically does do that for you. And usually what we're looking for is we want a p-value to be as small as possible and for it to have an effect less than 0.05. So in a lot of the things that we're going to see moving forward, we're actually going to look at p-value, and we want our p-value to be as low as possible. Because if a p-value is low, the associated z statistic is going to be like way out here, and then the p-value is going to be much lower. Questions, thoughts before we move on to making a conclusion? Okay. If there's anything you take away from this section, is that we want low p-values to confirm an effect. All right. So to finally interpret that, oops. Oh, I guess I don't really have an interpretation slide. But anyways, here with these results, because the p-value was 0.12, or because the z statistic of 1.19 was smaller than the critical z of 1.64, I believe, if I'm remembering correctly, we failed to reject the null hypothesis. And with this setup, tutoring actually did not have an effect on IQ. So that's our first statistical test done. I will tell you all that like in college, I did like a whole month on just doing these statistical tests. And for data science purposes, we really have only like one big application of doing statistical tests, which we'll talk about next week. But really with these statistical tests, we are mainly going to be just interpreting results a lot. Like none of this calculation we really have to do. Is all about, okay, we get a p-value, we get some statistic, what does that mean? So we'll talk about those more in context when we get to that stuff. Okay, so that was our first statistical test. We're gonna move on to some other stuff, but we'll come back to statistical tests next week. So another very important definition to remember, and only because, to be honest, only because of interviews, I've been asked this question like a good number of times, I feel, is the central limit theorem. It is the definition for a central limit theorem. The implications of the central limit theorem are actually really, really important to the whole field of data science and like making conclusions about the world. So therefore, that's why I think that's important, but you're not actually using the central limit theorem in practice. But let's go over this. The central limit theorem states that independent random variables summed together will converge to a normal distribution as the number of variables increases. So what does that mean? That's just saying that you have a bunch of random variables. So let's just say you have, let's say you have like a giant box of weighted dice. And you know, each weighted dice has some sort of probability mass function. The whole idea here is if you take all of their probability mass functions and add them up together, you're gonna end up with something that looks like a normal distribution. Another way of interpreting the central limit theorem is the distribution of sample means of any population as the sample size increases will converge to a normal distribution. One of your labs on central limit theorem actually does a really good demonstration of this. And the idea is that let's say you have some population of, I don't know, heights of human beings. So we're looking at heights of human beings. We don't know the underlying, we don't know the true distribution of heights. So let's just say we have this graph here to represent heights. So let's just say that this is height, and then this is, I don't know, probability, P. We don't know what this distribution really is. So very, very likely, maybe it looks like this squiggly line here, but we don't know what it is. Central limit theorem also states that let's say we take a bunch of samples. So let's just say I just randomly go to different countries, and in every country I go to, I take the height of 100 people at random. Distribution of sample means says that if I'm taking groups of 100 people's heights, and for each of those groups of 100, I just take the average and treat that as one data point, the central limit theorem just says that that will end up looking, and I'm just going to draw a small version here. If I take all the sample means, it will actually start to look like a normal distribution. So that's what the central limit theorem says. So why is that important for data scientists and pretty much anyone who does like experiments or statistical tests? It allows us to use sample statistics to make inferences or estimates on the population. Because a lot of time, when we're given data as data scientists, we don't have all the data. It's just impossible to have all data on everything ever. And so, just having subsets of data, the central limit theorem allows us to make conclusions on the world or on the population just using subsets of data. So that's why that's important. It's kind of like a conceptual important thing. But yeah, it's the reason why we can, use sample data and make conclusions. Questions about that?
Yeah, so to sort of flip this around, if someone says to you, how can you be sure that this, so say you come up with some sort of an analysis based on a sample population, and someone says to you, how can we be sure this is representative of the sample? The answer is because of the central limit theorem.
Yeah.
As long as the sample is appropriate, as long as it's appropriately sampled, right?
Yes, that's correct.
It's how the sample connects to the population.
Okay. That's right. To actually go even deeper, in topic, I want to say 16 or 17, I think 17, we're going to talk about, is it 17? Anyways, one of the coming topics, we're going to be talking about something called maximum likelihood estimation. And that will further drive home how we're allowed to say that, okay, this is what our sample means are distributed like, therefore, this is what our population is distributed like. So yeah, we will get more into this, I think next week. But yeah, definitely. A lot of reasons why, how can you conclude this based on your sample? It's because of the central limit theorem. All right, let's see what we have next. Okay, this is just another quick definition, because this is going to be used in some upcoming calculations. So sampling statistics. A statistic is sort of like a parameter that you calculate. So I know it's confusing because this is the field of statistics, but we say test statistic, we say Z-T statistic and all of that. But statistic is just another word of saying some sort of measure of a group of random variables. So a statistic that you use for samples, where before we had our, where is it here? We had our sample mean. Technically, X bar is a statistic of our sample. So this next one that we're going to talk about is the standard error. Standard error is the equivalent to a sample as the standard deviation is to the population. So it's the standard deviation equivalent of a population of a, oh wait, I'm not phrasing that right. Basically, standard deviation is the population, what standard error is to a sample. Yeah, okay. So standard error is very similar to standard deviation. The higher the number, the more spread out your data is. So same as standard deviation. While the standard error uses statistics, sample data, standard deviations use parameters, population data. So similar as what I was saying earlier. The calculation for standard error of a sample mean is, as I was kind of alluding to before with our Z-score for a sample, you just have to divide it by the square root of the number of observations in your sample. And often we can approximate our population standard deviation using our sample standard deviation in a similar way as the central limit theorem states that you're allowed to approximate things about the population using sample statistics. So this is another quick definition thing. Questions about this? Okay. So confidence intervals. So confidence intervals, we will actually not be, as a data scientist, you will not be asked to calculate confidence intervals, but confidence intervals are something that you will be asked to interpret in different contexts. So it's important to know the definition of a confidence interval. So what is a confidence interval not? A confidence interval does not contain 95% of the values. That is a common misdefinition, wrong definition. I, for a long time, thought that that was the case, but that's actually not what it is, because the confidence interval looks like a range of values, but it's not something that contains 95% of the values. Rather, it's a little bit more abstract than that. 95% of confidence intervals constructed in some manner contain the true population mean or parameter. So we'll talk about this more in the specific context we need to know this for. So don't worry about that too much. But a confidence interval is basically a range of values above and below the point estimate. So for example, let's say you're trying to estimate a population mean. You'll often be given like a confidence interval for some population mean. And that just says that it's a range of values above and below the point estimate population mean that captures the true population parameter at some predetermined confidence level. So basically the whole idea is, let's say you calculated, you're estimating the population IQ, and we estimate our population IQ to be 100, right? But we don't actually know the true mean of the population IQ because it's not possible for us to make every single person on Earth take an IQ test. If we are given some sort of confidence interval for population IQ, so let's just say a 95 confidence interval would be like maybe plus minus, let's see, 16 times 3, if I use 16, okay, so plus minus 50. So let's just say I have a 95% confidence interval of my IQ being 100, and the interval is roughly 50 to 150. That's just saying that 95% of confidence intervals constructed in this same manner for a bunch of different estimated population means will actually contain the true unknown population mean. So I understand that it's very, very abstract. It also took me a while to like sit down and think of it. I recommend the Stats Quest video if you are curious and want to like get a better like drawn out explanation. There are different ways of calculating confidence intervals. It does depend on your underlying distribution. So with that IQ example, we had the assumption that the underlying distribution was a normal distribution. So therefore, it's mean plus minus the margin of error. So the mean of 100 plus minus margin of error, we were saying 16. So margin of error, as I was saying, depends on your underlying distribution. So if you know the population standard deviation, therefore you're using an assumption of a normal distribution, your margin of error is calculated like this: your z-score times your standard deviation divided by number of things in your sample. Again, the calculation is not super important, although your labs do have you calculate some confidence intervals. Every time we use a confidence interval, they will be spat out at us, and then we just have to interpret them. Any questions about this? I would say the most important thing to take away from this is if someone says, this is our confidence interval for estimating this, you would just have to interpret it as 95% of confidence intervals constructed in this manner contain this true value. Not it contains, there's a 95% chance that it contains this value. Okay, questions? All right, so the last thing I want to talk about is the t distribution. So far, what we've been talking about is the normal distribution. Something that looks very similar to the normal distribution, but is not, is the t distribution. So this is a primer to our next series of tests that we're going to talk about. We're going to talk about t-tests at our next study group. And it's basically used in cases where we do not know the population standard deviation. So when we did a z-test, like what we did earlier, when we did a z-test, we did know our population standard deviation. Like in our last example, we knew, or we were just given the fact that our population standard deviation was 16. But when we're using t-distributions, we do not know that population standard deviation. So several other calculations will need to be made. So t-distributions are used when we don't know the population standard deviation. Instead, we're going to use a new parameter known as degrees of freedom. Degrees of freedom is often, what's the word? Abbreviated. Yeah, it's often abbreviated as DF, which I know is confusing because DF is data frames for us. But if you see DF in a statistics sense, it is degrees of freedom. The whole idea here is the more degrees of freedom that you have, the more like a normal distribution your t-distribution will look like. So whereas before our normal distribution was characterized by mean and standard deviation, our t distribution is characterized by our mean and the number of degrees of freedom. And the number of degrees of freedom is n minus 1. So based on this, we know that a t-test is usually dealing with samples, a lot of samples being used. So n is the number of observations in your sample, and degrees of freedom will just be n minus 1. So if we take a look at this, and I know it's kind of small, in this example, the blue line is a normal distribution, and the red line here is a t distribution with 1 degree of freedom. 1 degree of freedom means that there are only 2 observations in that sample. So you can see it looks quite different. But as you increase your degrees of freedom, it starts to approximate a normal distribution. This is not super relevant to us, but kind of good to know. Whenever you have, and it's kind of agreed upon in the stats community, that if you have a sample size of above 30, it's pretty safe to go with a normal distribution. But yeah, something that's good to know. We'll talk about this more at our next study group as well. But just like how we had the z-score table for our z-scores, there's actually a t-table as well over here. But I'll talk more about how we read and interpret this at our next study group when we do some actual t-tests. All right, so that's our t-table. And then also, this is just how you calculate a confidence interval for a t-distribution. You can see here, it's just the sample mean plus minus this measure of, what am I trying to say? What's the word? Margin of error. Yeah, I was blanking on the word. Plus minus the margin of error, which is calculated slightly differently. There's quite a few things with this calculation, but again, I do want to mention that we will never have to do this calculation by hand. There is a method that helps you calculate the confidence interval, so we don't have to do that. But just want to show you, this is to show you all that the calculation will depend on the underlying distribution. Cool. Any questions? All right, well, this is our last slide, so I'm going to stop the recording over here.